So I mentioned this previously, but I'll mention again. For the one-dimensional case, the first and second derivatives provide us with important information on searching for optima. So, for example, the first derivative will tell us the steepest trajectory, and it will also tell us when we have reached an optimum value. The second derivative, in the one-dimensional case, tells us whether we are at a maximum, and this would result in the sign of the second derivative being negative, or if we are at a minimum, where the sign of the second derivative is positive. So how do we extend this to some sort of multidimensional problem or case? Well, we may think that if both the derivatives of our function with respect to x and y, that is df dx and df dy, are less than 0, then we will be at some maximum. Sorry, this should be the second derivatives. So if they're both less than 0, we may think that we are at a maximum, but it turns out that this is not true. So we need to figure out another way of identifying optima using the first and second order derivatives. And it turns out that we can use something called the Hessian. That is second derivative of f with respect to x multiplied by the second derivative of f with respect to y minus the second derivative of f with respect to both x and y squared. And if if our Hessian is greater than 0 and second derivative with respect to x is greater than 0, then we are at some local minimum. Local is an important keyword here. If the Hessian is greater than 0, but our second derivative of f with respect to x is less than 0, then we are at another local max. And if the Hessian is less than 0, then we are at a saddle point. Okay, but now this formulation of the Hessian should look familiar to you. And it turns out it's actually just the determinant of a matrix consisting of our second order derivatives. That is H being the matrix d2f dx squared, d2f dx dy, d squared f dy dx, and d squared f dy squared. And this is known as the Hessian.